Hello everyone, welcome to today's quantum space-time seminar. Today we are very happy to have Akhil Sivakumar from ICTS, and he's going to tell us about fluctuating hydrodynamics via holography. Over to you, Akhil.
Hey, first, so I'm audible now?
Yeah.
Okay. Hey, first of all, thank you guys for giving me this opportunity to talk at the QC seminars. And I hope all of you are doing well during the pandemic and so on. So today I will talk about fluctuating hydrodynamics by holography, which is a program we have initiated over the last 1 or 2 years, like trying to include the effect of improve the fluid gravity correspondence kind of calculations, basically, or like any real-time calculations in holographic systems using some recent techniques in real-time holography. So there are various projects I have done in this line of work, but like I will be mostly talking about this particular work mentioned here, and then and another work which is ongoing. So this is an extended list of collaborators from these two works. I have Jewel Ghosh, Loganayagam, who's also my advisor, Siddharth Prabhu, Mukund Rangamani, Vishal, Temple Hale, and Julio Viruta. So let me start then. So we'll start with an introduction. So the ADS-CFT relates the hydrodynamic excitations of the holographic CFT to the long wavelength deformations of the blackbrane. And over long distances, so this program, which was initiated around like a decade, more than a decade back, called the fluid gravity correspondence, finds that over long distances, holographic plasmas behave like dissipative fluids, which is a standard expectation from the field theory, and then in the bulk, these dissipative fluid modes correspond to quasinormal excitations of the blackbrane. And there are two ways to think about it. In one, it helps you calculate. It lets you think of the long distance behavior of a strongly coupled system, and like in general, which is a holographic CFT. But in general, then we know the holographic CFT expectations have been setting the norm for all strongly coupled calculations in the field theory since ADS-CFT, right? But in the bulk, from the bulk side, then it lets you map the small deformations of the black hole solution to a fluid. So the correspondence goes either way, and she gives you a way to think about black hole solutions, slightly deformed black hole solutions, and then also the fluid long distance behavior of the strongly coupled CFT. But then we know dissipative fluid behavior is only an approximation to a more complete picture of fluctuating hydrodynamics, where you really have to start thinking about fluid hydrodynamics beyond the Navier-Stokes description or as a set of partial differential equations, but rather as a field theory where you can account for the effects of fluctuations, statistical fluctuations of the fluid components, or even the microscopic fluctuations feeding into the fluid modes as some stochastic noise. And the fact that these microscopic modes will couple to the fluid and show up as noise is just a consistency condition, right? Because we know fluctuation dissipation relations would say a dissipative system would also see fluctuations, because if you're dissipating into something, that something would kick you back at sometimes. So in the bulk, we then in the bulk this is entirely again motivated from the bulk perspective, like because the blackbrane should Hawking radiate, which is required for the quantum mechanical consistency of the bulk. Because if you're dissipating into the black hole and then you consistently study the horizon, we know that the outgoing modes are turned on and the Hawking radiation is turned on. So our objective is to study this effective field theory, where you study hydrodynamics as a field theory where you have both dissipation and fluctuations, and also like as we go forward, when these effects start talking to each other. So from the field theory side, we would have a fluctuating hydrodynamics description. But then what this gives us from the bulk side is that you can now think about black hole solutions where you have modes ingoing into the horizon, the quasinormal modes, and then the black hole reacts by Hawking radiation. But then these effects talk to each other and influence each other and so on. So this is so I guess in the way I said, fluid gravity correspondence like gives you a way to think about deformed black hole solutions as fluid configurations. This kind of talk lets you think of interacting Hawking radiations of the black hole as configurations of fluctuating hydrodynamic systems. So that's the general motivation. And like this paradigm, it's the easiest way to like appreciate this paradigm is by like thinking of the standard example for such a system, which is a Brownian particle in a fluid, say a pollen in air or something, right? So at low energies, you look at the system. What you see is there is air, which is a fluid, and then the fluid has its excitations like the pressure waves or like the shear modes and so on. And then there's a Brownian particle which probes this fluid. But then what the fluid does to the Brownian particle is that it makes the Brownian particle dissipate energy. Like you throw a Brownian particle into a fluid, it decelerates. But then it is the same consistency requirement. By the same consistency requirement I mentioned earlier, like the Brownian particle is Brownian because the air molecules randomly kick into it, which are the microscopic excitations. But you don't really but to study the EFT really, you don't need to think of air molecules all the time, right? So in the lesson here is that the low energy description is an open EFT where you have the long distance fluid modes and the Brownian particle, which form an open system and interact with the microscopic modes of the system. In other words, we may integrate out the fast or microscopic modes of the system, which I will be referring to as Markovian modes in this talk. And in our description, we need to retain only the slow modes of the fluid and the EFT. And the slow modes I will be referring to as non-Markovian modes. So for the purpose of this talk, Markovian mode are modes which don't show long distance correlations, while the fluid modes or the slow non-Markovian modes are the modes which show long distance correlations. And the objective is to then study the evolution of this open system.
So, sorry, Akhil. This is Sandeep. I'm sorry I joined a little late. Hi, please excuse me. But there's something just to ask you, which I'm not sure about, which is if you'll be interested in the dynamics of Hawking radiation interacting with the black hole, then is it enough to just consider the hydrodynamic modes of the black hole for that interaction? That is, to draw the analogy, I thought you were saying the Hawking modes, the Hawking radiation modes will be like the pollen particles, and the fluid mechanics modes will be like the hydrodynamics modes. So it wasn't clear for Hawking radiation and so on. I mean, if I'm going to keep track of the black hole degrees of freedom, I might think I have to keep track of all the degrees of freedom which make up the entropy of the black hole. One qubit per Planck size of the horizon, rather than just the hydrodynamics.
So I think you said I think you misquoted in the sense Hawking radiation corresponds to the particle, but I'm just saying there is a Hawking radiation for every mode coupled to the system, which is that the modes corresponding to the fluctuation of when that particular excitation mode fluctuates. But I guess the second question is whether I have to take care of all the degrees of freedom, right? Sorry, then
in terms of your analogy for black hole physics, what is the polon particle?
Polon is something you like introduce into the system, right?
Okay.
It's a probe. It's a probe, and you can at some order, if you think of probes as coupling to operators of the system or the excitations of the system linearly, it's a source.
Okay, but all I'm saying is it has to be a cruder, so to say, probe than the details of the Hawking radiation, right?
The thing is, you can think of a probe which couples to any kind of excitations of the original fluid, right? And then the fact is, as these excitations oscillate, as these excitations fluctuate, the probe dynamics is affected. Now the question is whether the probe dynamics, whether these excitations of the original system or modes of the original system showed long-range correlations or not.
Okay.
So the fluctuations and the fact that these excitations can fluctuate, the original modes in the system fluid can fluctuate, and that the probe can dissipate energy into them is universal. It doesn't require like we don't really talk about any particular kinds of states, right? The fact is anything coupled to the black hole background is Hawking radiated by the black hole, and anything living in the black hole background would fall into the black hole. Is that
okay? No, I think I understand better as you go along. Okay, sorry, please go ahead.
Yeah, sorry, one quick comment on this. It seems to me that at least the part of the probe that is outside the horizon should be easy to deal with what Akhil is saying, right? Because that's where the glue ball degrees of freedom rather than the gluon degrees of freedom.
Yeah, but it's not clear to me, Shiraz. I mean, I should just wait, but it's not clear to me if you're thinking of the details of the gravitons being emitted by the black hole, you know, in all detail in terms of the state which is being produced, then clearly hydrodynamics will not be enough. No,
clearly not. So you want some average. It's like average fluctuation or something like that.
Yeah. So that's what I was just trying to understand. So some average property like that, like yours.
But these, I mean, you're talking about some microstate kind of statement.
Yeah, I just wanted to understand. I think
those are non-perturbative in entropy, surplus, and so on, right? Like, I mean, I'm talking. Isn't it like when those details, if I want to really access them, those are like way suppressed than like the leading 1/c, the C of the CFT kind of suppression.
Yeah. No, I'm sorry. I think I should just wait. I think I had in mind what Shiraz was saying, that you there's some kind of an average of the detailed properties that you will be looking at, and it will probably become clearer.
Yeah. So I am looking at the fluctuations which arise at the leading thermal behavior.
From just the leading thermal. Okay. By coupling some probe, some operator, say, to the fluid, which represents the hydrodynamic degrees of the black hole.
Right.
Okay, that's fine.
The probe couples to more than the hydrodynamic degrees of the fluid. So that's a pointer. The probe, when you say hydrodynamic degrees of the fluid, like I really mean the modes with long distance correlations. So the shear waves and the sound waves, or some gallstones and so on of these various hydrodynamic particular models. But then there are also modes which decay faster. So if you just say purely go to the ADSCP dictionary and talk about it, there are like metric perturbations in the boundary which don't show long distance correlations. So you could couple probes to them as well. So that's what I mean by the microscopic modes, which do not fall into the hydrodynamic kind of modes, are still can be coupled to the probes.
I see. Okay, but please go on. I think I'll understand better.
I guess what Sandeep is asking is, if you have these hydrodynamic modes or these probes which coupled to the shear or the hydrodynamic modes, what analogy or what correspondence they would have with the Hawking radiation of the black hole?
Sorry, could you state that again? Sorry.
You're saying that these modes are coupling to the shear or the viscosity and things like that, right? They're long range modes.
And also the short range modes. I could couple probes. So I haven't, as of now, I haven't like mentioned coupling a probe to the hydrodynamic modes. But what I'm saying is, like, you want a description of the fluid, which necessarily includes the hydrodynamic modes. But then you could introduce probes into the fluid, which is that you could add particles into the air. And then both these kind of things, both the introduced probes and the hydrodynamic modes, suffer from fluctuations or noise, which is a fact that there are microscopic excitations in the system.
Okay, maybe if you just explain more, it'll be clear. Okay, go ahead.
Okay. I guess so that's a broad motivation, and so this is the and once you introduce this question, right? Like I talked about studying the system, and like basically I don't know if it was clear, but like I kind of motivated that you can have a system where there are modes with long range correlations and there are modes excitations without long range correlations. And to study the system in the low energy EFT, in the hydrodynamic limit, you can essentially forget about the short scale modes. So that the whole sentence consists of two key steps, which is first of all, how do we study such open field theories, right? And because like this falls outside the standard setup of Euclidean QFTs, because I'm talking about real-time dynamics of the systems. It also falls outside the formalism of Lorentzian QFTs, because I have to now study like systems which are not characterized by states transition to states, right? It is like in other words, I can't work with just time ordered correlators kind of setup. So we need to motivate a set right field theory formalism which captures these systems or the open field theories. And then second part is like, how do you indeed separate out these dynamics, the fast and slow dynamics, and selectively take out only the fluid modes. So like that's a broad motivation, and then like this is the plan for the talk. So first I will like motivate open field theories as defined by Schwinger-Keldysh path integrals, which I'll explain, and then we will describe a way to study such path integrals from the gravity side. Then I will talk about what our results on how to make the separation of slow and fast modes, which is distilling out these fluid modes. And then I will object the central. I will motivate the central object we motivate in these works, which we call the Wilsonian influence functional, which is kind of an effective action for the fluid modes, where of the original system. But then you have, it's a generating functional for the fast modes, the short distance modes.
Akhil, one quick question, please.
Yeah.
The field theory in question that you're studying is not coupled to some other noise. As a field theory, it's a closed system. Right?
As a field theory, it's coupled only to these probes.
Right. So if suppose for a moment I switch off the probes, say there are no probes, then the field theory is just a closed system by itself.
Not really, right? There are the black hole kind of microstates. If you think about the states which you don't study in the supergravity, right?
No, I was saying as a field theory, it's a closed system in itself. Not because because when you like say you derive the Schwinger-Keldysh action for the fluid modes without any probes coupled,
it does have the you should be familiar with this from what Chandan talked about and so on. It does have the RL couplings, which says you have integrated stuff.
As a field theory, no fluid dynamics, just field theory. Suppose I want to compute some correlation functions of the stress tensor on some contour you prescribed for me. I'm not saying any fluid dynamics yet. Just as a quantum field theory at finite temperature, it's a closed system.
I don't know actually what you mean. Like, what do you mean as a quantum field theory at finite temperature? Like, what field theory?
N equals 4 angles.
But I don't. Okay. It's the statement is like when in the okay. I guess N equal to 4 angles is like closed system, but like in the limit I study, yeah, okay, like when you study hydrodynamics, it does have dissipation into the microscopic waves.
That's fine. Okay. So sorry if I just
maybe I didn't understand the.
No, I first wanted you to agree with me that the field theory itself is closed. This you agree with, right?
Yes, I agree. N equal to 4.
Okay. So, yeah. Now, so suppose I wanted to compute some correlation functions of the stress tensor in N equals 4 angles on the contour that you will prescribe. Correlation functions of the stress tensor in N equals 4 angles. This is some correlation function I'm computing in a closed system.
Yeah.
And then you can make whatever approximation you want to make, but you're computing the correlation functions of stress tensor in a closed system.
Yes.
Okay. So then I'm confused a little bit about. I mean, then maybe you will make some approximations to compute this, but I'm a little confused about this. The user, for instance, if there are some properties that correlation functions at finite temperature in a closed system must satisfy, some exact properties, some unitarity type properties, for instance, then whatever you compute must also satisfy these properties, right? So I'm a little confused about your use of the word open for this thing.
So this is a bit more stark from the bulk, right? From the bulk, you have a black hole, and you do dissipate into the black hole. So would you say the same thing about the fluid modes as well? Because I mean, so I am really thinking about the fluid modes, I guess, which don't really excite the black hole beyond a point. So
yeah, I just want to say that if there are some properties that correlation functions of stress tensor must obey in a closed system, then your answer should obey them. And then the use of the word open is some words.
So what kind of properties do you have in mind?
I don't know, unitarity type properties, something which says that.
But then that would really require me to like do a bulk. So say if I'm implementing your question from the bulk, that would really require me to consider the full string theory in the bulk. Want it?
No, yeah, right. The quantity you're trying to approximate obeys all these properties, and then your approximations may or may not maintain some of them. I mean, what I'm saying is, I suppose, some trivial, obvious thing. I just wanted to get the framework here.
See, right, even within, okay, maybe if the question is even within the approximation, even within the even within this low sector of hydrodynamic excitations, the quantities I compute will show a particular property which corresponds to microscopic unitarity. But I kind of view it as a consistency of the
that's very good.
Of the analytic property of these correlations and so on.
Yeah, I just want to contrast this with actually coupling N equals 4 system to some path. There actually the information will actually leak out into the path. It will not be present in your original N equals 4 system. So that seems distinct, a distinct kind of openness.
Yeah, that is a distinct kind of openness, and we don't really do that. We don't couple N equal to 4 itself to a path.
Yeah, and there will be some properties that will be obeyed when you don't couple N equals to 4 to a path. That will be obeyed. That should be obeyed even in your hydrodynamic approximation.
Yeah, okay. That I agree.
Okay, thank you. Yes.
I have a question. Your hydrodynamic system is a system in, say, ordinary 3+1 dimensions, right?
General dimension as of now, but maybe we can think 3+1.
Some D+1 dimensions.
Yeah.
So, as such, everything should be describable by physics in that space-time, right? And whatever you're saying is dual to that system, should be a system which gives you an alternative dual description. So I don't understand what you exactly mean when you say that your system is coupled to the dual system in a sense that that makes it open.
No, I didn't mean my system is coupled to the dual system.
But you're coupling your degrees of freedom to the black hole, right?
No. Like, so I have the fluid limit of the, say, n equal to 4, and I could introduce probes to them. So that's there. And then sometimes these, especially if someone like challenges me about dissipation and so on, like I guess it's more evident. At least for me, it is kind of more easy to think of what happens in the bulk. So maybe I kind of misspoke and confused you guys. But like I don't mean to couple the boundary system to the bulk.
Okay, go ahead.
So sorry, Akhil, I know you must go on, but just as a follow-up to some of this discussion that Shiraz raised, so then can I summarize, at least from the field theory point of view, that you have a field theory which is closed, so to say, the field theory is by itself, and the general issue is, let's say fluid mechanics arises at long wavelengths. You want to think of it as an open system to the extent that the fluid modes are interacting with the rest of the degrees of freedom of the field theory. Okay, I understand. And now just allow me to say one thing, but you correct me. If this was a more standard problem in field theory without dissipation and so on, where we had a Wilsonian effective theory we were constructing at long distances, we would all know how to construct the low energy effective theory. But you say in the context of fluid mechanics, this is a general issue. That is, because you have dissipation, etc., how to construct that low energy effective field theory itself is unclear. Is it because it's interacting with the rest of the modes of the quantum field theory and it has dissipation and so on? Is that the general issue then, if I've understood?
Okay, so
or just go on if I'm, you've got a long ways to go, but I thought this was the upshot, that this is the general kind of issue you're after.
So one statement is like, see, if you just study a field theory, you have to extract out the collective modes which behave like the fluid. But then as we know from the fluid gravity, it is clear that for the strongly coupled plasma at the boundary, like you can just study the stress tensor correlations and stress tensor, and it predicts the fluid behavior. So the bulk gives you the collective modes just as the gravitons and so on. But if you're saying, if you want to study from the full microscopics, how to extract out the fluid, in the bulk, it is clear that it's the leading behavior of the graviton fluctuations and all those massless modes and so on. But from just a field theory, it is not. It is harder, way harder to do it, especially when there's no strong coupling and so on.
Oh, okay. Go ahead. Thanks.
Sorry, Akhil. One more just related question. So, is it that, I mean, this thinking of description of the effective low energy modes for a thermal field theory as open field theory, is this something standard, or this is something that you are introducing now? Maybe this is
I am not introducing it, right? So because like fluctuating hydrodynamics is the thing, is a formalism we can motivate generally, because once you have hydrodynamics, like it's very clear if you think of the Brownian particle example, right? You can think of the particle drifting with the drag, but then the correct description is a Langevin equation where you have to couple a noise, because that's the only quantum consistent or the statistical fluctuation consistent thing. Because there are these Brownian, which is the Brownianness, which is suppressed, but then
so the open field theories are something like the Langevin equation.
So the open field theory is a field theoretic, like this path integral kind of view to Langevin equation. So your question is, where am I motivating fluctuating hydrodynamics or like the open field theory perspective on it? I think I'm not doing I'm not doing it either for the first time, because this perspective is like has been around for like at least like 10 years, I think.
Okay, thank you.
So what is really novel is that like we are working with certain new techniques on the gravitational side, which lets us really go do these calculations in the bulk, which wasn't possible before. And then there are some subtleties even with other people who have tried to calculate these quantities using the same gravitational, say, saddle. There are some subtleties these people overlook, which is like which are like the harder technical part of the talk, which I might like briefly mention. But the viewpoint itself as open, maybe the word itself is not used as open field theory, but the fluctuating hydrodynamics is a perspective, is a formalism which has been motivated for a while back. Yeah. So let me so if the motivation is clear, like let me go to the first point in the plan, which is I'll explain Schwinger-Keldysh path integrals and like how they relate to open field theories, right? So the point is that open systems are described with reduced density matrices. So the states of the open systems like form mixed states, and then you don't really think of them as states, the usual states transitioning to states, but rather initial density matrix evolving. And then you can think that the such states have a more general class of correlations than the usual time-ordered correlations. Where you think of the density matrix has been, where the density matrix is sourced from its either sides by unitaries, which I have indicated here as unitary JR and unitary dagger JL. And this wider class of correlations are captured by a generative functional defined like this, which I call the ZSK, Schwinger-Keldysh generative functional. So if you want to think of it from the path integral perspective, these correlation functions are generated by doing a path integral on a closed time contour. So there is some initial state. Is my cursor visible?
Yes.
Okay, thanks. So there is some initial state which is marked by this violet point, sorry, and then it evolves forward, and then you may apply with operators as you evolve, and then you have to implement a trace condition here, and the trace can be done at the future point, and the bra part of the density matrix then is approached as you evolve backwards. So these are basically like this is basically the in formalism or closed time contour formalism, where you think of the path integral as being done on a contour which goes all the way to the future and comes back. So I will call the ket part of this evolution as right, or usually indicated with various R subscripts, and the bra part of this evolution as left, which is indicated by L subscripts. And further, if you're like, we know thermal systems can be prepared using a Euclidean path integral, right? So further, there's the state preparation for thermal systems can itself be implemented via a path integral if you attach a Euclidean segment to these contours, where you identify these red spots. So that's what I've indicated here. So what you see is like once you go into this formalism, there's a natural doubling of operator content, a copy of any original field which lives on either sides of the contour. Then the contour order.
Sorry,
so the
what is JL and JR? What are JL and JR?
JL and JR are the sources for any unit. So you can define unitaries acting on the system as some exponential of some source J times some operator. So the JL and JR are the sources which act on the either side of the right and left side of the contour.
Okay.
So there's a natural doubling of operator content as you go to this formalism. Any field is doubled to a field on either side of the contour. Then the contour path integrals create contour ordered correlations. So right fields are time ordered like the usual fields, and then the left fields are anti-time ordered. And like I said before, like these fields should be identified at a future most point beyond which you don't plan to act with any operators in your correlation. And then you can define the connected part of this correlation as some action, the Schwinger-Keldysh action, which should have a structure like this, which should generally have a structure where it is functional of the right sources, then the subfunctional of the same same functional with the left sources subtracted, and a functional which is a mixed functional of these two sources. So the point is that if you could think of, so now if you want to study an open field theory, right? The general quantum mechanics expectation is that you start with the full density matrix, trace out degrees of freedom, right? So you could think of this being done in the field theory. You could start with the density matrix of the full system, put it on a Schwinger-Keldysh contour, and then start integrating out fields. So you could say in a simple model, you have the fields you want to integrate out and the fields you want to retain, which I call the bath and the system, respectively. So if they're linearly coupled or something, essentially, like you can think of it as you can think of the resulting Schwinger-Keldysh action after integrating out as this Schwinger-Keldysh SK here, where the JRs and JLs are replaced by the system fields, or the fields of the open system, and S influence functional, which then couples the fields on either side, the Ket and Bra copies of the field, which remember which is not present in any original action, any unitary microscopic description. There's only one copy of a field. But then now, once you integrate out stuff, you start generating these terms of the action which couple these two copies, and hence these are termed as influence functional, which kind of indicates they capture the influence of microscopic degrees of freedom. So then there are like these collapse rules on the Schwinger-Keldysh action.
Sorry, Akhil.
Mm-hmm.
This S is a function only of sources, right?
S is a function of sources, but when you come to the open QFT, I'm saying these sources are to be interpreted as the I defined S from the generative function. True.
Okay, excellent. So if I computed this S for a single harmonic oscillator,
mm-hmm.
Won't I have this off-diagonal piece as well?
No, you won't have the off-diagonal pieces.
Really? I mean, why isn't there some coupling between?
So what do you mean? You take a harmonic oscillator and then you
turn on J for X. J is some source function for X.
So you put the harmonic oscillator on the contour. You write force it with F right, X right, and F left, X left.
Yes.
Then it's clear that the action is just the P square plus X square of the right. I mean the X dot square plus the minus X square of the right, X dot square of minus X square of the left, and then these forces. So the action clearly factorizes. You indicate out, you don't.
But your X at the joining point has to meet up. Your field meets up at that middle point, right?
Oh, okay. I guess I misspoke. Okay, right. You calculate the generative functional. Yeah, yes, right. Exactly the point. So that's as if like you're integrating on the harmonic oscillator, thinking of it as influencing these sources, the F sources. Yeah, it does create the RL coupling. Yeah.
Right. So any system that's a simple harmonic oscillator will have left-right couplings.
The generating function of the harmonic oscillator would have left-right couplings.
SIF would be non-zero even for a simple harmonic oscillator. It's not some, right, fine. Okay, thank you.
So the system doesn't have RL couplings. That's what I mean. If you, of course, if you couple sources, you will and calculate the generating functional, it will have RL terms.
Classical action splits as S right minus S left.
Yes, that's my claim.
That I agree. But there's no such statement for generating functions. Right?
There's no such statement for generating functions.
Okay, thank you.
So yeah, generically Schwinger-Glish action looks the connected part of the generating function looks like this. That's mixed terms. And I'm just saying that once you think of it as obtained by coupling fields where you replace this J's for the fields and integrating out the original fields, these are signatures of some that this is a diagnosis for the fact that something has been integrated out. So then there are consistency conditions for any Schwinger-Glish action.
Akhil, I have a question.
Yeah.
So let's say we calculate some 2-point correlator phi r phi l. What does that physically correspond to?
Phi r phi l is simply a correlator, like Shiraz mentioned. It's just a correlator saying that there is a future boundary condition which identifies these fields. But then phi r phi l itself doesn't bring in any new information, in the sense that phi r, say like you had a phi r inserted where my cursor is now, and phi l inserted here. The boundary conditions imply that you could this is same as a phi r correlator here. So phi r phi l correlator, based on whether which of the time arguments is bigger, will give you either the simple Weidmann function where it's just a Weidmann function. It doesn't have any particular physical meaning. It's not a phi r phi l. Maybe what I'm saying is phi r phi l is not a Green's function. It's just a correlator. Maybe you meant something more specific.
I think maybe the question was, is it related to can you build retarded correlators and advanced correlators out of these things?
Okay, I see.
And as you know, the answer is yes, right?
Yeah, the fact is you can make advanced and retarded correlators as combinations of RL correlators, LR correlators, RRs and LLs and so on. That's true. But RL itself, it's just a correlation function. Which would mean that it's just a Weidmann function, which is just a correlation function. It doesn't correspond to any particular propagator as yeah.
Okay.
They would be obtained by differentiating
I just
the J's.
Sorry.
The correlators would be obtained by differentiating with respect to the J's, the actions, the path integral.
Yeah, you take the ZSK and differentiate with JR and JL, and you generate or the operator R, operator L correlators. Yes.
Okay.
See, these are you can just think of this as generating functional for a more general class of path correlations, which are not just time ordered or just anti-time ordered, but you can have a correlation function where you have a operator sequence arranged such that you can change the ordering of time once. So usual correlators have only the phi's at first second, second, third second, the time ordered correlators, or the anti-time ordered correlators would have phi's at 5 seconds, 4 seconds, 3 seconds, right? But these class of the correlation functions generated from here lets you change the ordering or bend the ordering once. So you can have correlations where you measure phi at 1 second, 2 seconds, 3 seconds, but then again 2 seconds, 1 second. So that's all the point of these correlations are. And the statement is like, if you want to study retarded correlations, they belong to this class of correlators, or as like they form like as some combination of this class of correlations.
Another thing I'm confused about is I guess I am misunderstanding this, but I thought that the JRs and the JLs were defined at the ends of the contour. I mean, they were.
No. This is the. Are you talking about the? Sorry, could you say again?
In this particular contour, where are the JRs and the JLs?
They are like spread through all along this bent line, the full contour. The R's have support. R's are defined to be the sources with support only on the top part, the CR part, and L's are defined to have support only on the CL part.
What I'm confused about is you said that they represented bras and kets. So
right,
represent bras and kets.
They are the JRs and JLs are the forces on the fields acting on the ket Hilbert space and the bra Hilbert space.
Okay.
Does that?
Yeah, I guess, yeah.
Okay. So if this part is clear, so let me move on to the Schwinger-Keldysh gravitational saddle, which is the gravity way to implement this path integral. Because we know from standard ADS CFT that like if you want a particular CFT manifold, the path integral on that CFT manifold corresponds to general gravitational path integral on every ADS space which asymptotes to that, right? So therefore, like you would expect that the gravitational space-time itself should have a geometry where it asymptotes to this contour, where there's a bent contour, and in particular for the thermal state bent contour with the Euclidean circle attached, right? So that would be the right saddle, that would be the right geometry where you can do ADS-CFT computations and generate these thermal Schwinger-Keldysh correlations, right? And such a geometry, like a way to think of such saddles, was proposed by Skentris and Bandris from their work from a while back, where they think of like these saddles as geometries where you have two black hole exteriors. Like there are two copies of black hole exteriors, say the shaded region in this Penrose diagram, two copies of them, but then glued along at the horizon. So the horizons are identified, and then you can think of the thing that at an initial time there is an additional Euclidean part. So the diagram on the right side, where this part is supposed to show the Euclidean black hole, which is a cigar. And then you can see that the highlighted red part is the boundary, which looks like the Schwinger-Keldysh thermal contour. So there's some rough picture like this, and then
I have a question. Apart from this is just the time direction, right? I mean the dual.
Yeah.
So
yes.
there's also the space manifold. So
there is a space manifold which is attached at each of these points. That's there. Yeah. But that doesn't show anything non-trivial, right? In the CFT or the and hence not in the bulk.
Okay.
Yeah.
Akhil, sorry, I'd understood this once a little, but I'm not as sure now. I mean, is this Kenderis contour basically taking the Euclidean part to generate the thermofield double, and then giving some Minkowski evolution to both ends of the thermofield double, or what? Is it like that?
So it's not a thermofield double, because thermofield double would mean that you only have the half of the cigar, right?
Right, but I was thinking then you trace over one half or something. No. Okay. Maybe not. Huh?
See, okay. I don't think it's thought of like that. You do have the full cigar, so you kind of slit the cigar and then evolve the two sides of the slit on a Lorentzian thing.
Right.
But the thermofield would, yeah.
Okay. Sorry. Here you have the full cigar. Just
I have the full cigar.
Tip. Yeah, one tip you take off into Minkowski and bring back, right? That's
yes.
what you do.
Yeah.
Okay, sorry. And that has a, then that edge on the boundary can come out of a full gravitational saddle point, huh?
You would think there should be some gravitational saddle point which does that, right? I'm not saying there's a picture like that which is complete, but like, yeah, something like that. Yeah.
I see. But actually it is not like one can find such a saddle, huh?
Actually there is no saddle unique, described as a single solution, but then, I mean, it's also, there's no solution like that.
Okay.
It's a saddle of some mixed signature, right? So, their prescription was to basically do gluing, right? Take this, cut open Euclidean and glue and so on, which imposes boundary conditions and matching and so on, and then implements the thermal state.
Yeah, I guess what I was saying was, but you must go on, and this I don't think adds much. But if you take your boundary, which is almost a closed circle, and chop it in half, that closed circle, then I think then at that instant of time, you create the two copies of the thermofield double. And that can be your bra, and then you can have a ket or whichever way, which now, because you integrate, you close one end of that hemisphere, you have integrated over the thermofield double, and then you're left with just one end. I'm only saying this because the thermofield double has a nice gravitational dual, right? And can we think of this as sticking two of those on top of each other and integrate over the geometries in between? Sorry, go ahead. Or just, you can go ahead. I just, okay.
Let me maybe skip and maybe.
No, it doesn't matter. Go ahead.
Yeah, thanks.
I have another question. You're saying that the spike is in Minkowski space and the circle is in Euclidean space, something like that, are you saying?
Yeah. So the lower part here, the cigar kind of part is of Euclidean signature, and these fins. There's a double fin here, which are like the exteriors of Lorentzian black hole.
But I'm confused. Aren't they in the complex? Shouldn't they be understood to be in the complex plane or something?
So see, first of all, this is a very cartoonish thing which we don't really have, or we don't know how to implement and so on. But you're right that the time on the Lorentzian segment and the Euclidean segment is supposed to be of mixed complex signature.
Yeah. So that would then alter your your bulk geometry also in a certain. I don't know.
Yes. The bulk geometry has mixed signature. That's right.
Okay.
Yeah. So this story about the Skendris, Vandris, and so on is like a bit of the history. So what we really work with is a more recent proposed prescription, which kind of implements the thermality of contours calculated by ADS-CFT in a more efficient way, and for certain reasons, and for certain reasons, this you can only do a proper calculations of say interactions and Witten diagrams in this saddle, and the main point is the saddle implements the gluing at the horizon and defines the gluing at the horizon in a more clear way. Okay, so this proposal defines the Schwinger-Kelly saddle as an analytical continuation of the Lorentzian ADS blackbranes by complexifying the radial coordinate in ingoing Eddington-Finkelstein coordinates. So this by Crosby, Glorious, and Liu. So the main point here is that there's a complexification of the radial coordinate, and the prescription is closely tied to ingoing coordinates. So let me just describe it in a bit more detail. So the CGL prescription and their argument goes somehow like this. The point is, in ingoing coordinates, we know quasinormal modes are analytic at the horizon, right, as a function of radius. And then the Hawking modes have branch cut singularities. The CGL prescription says that, okay, what you can do to resolve this singularity is that, like, naively deform the radius coordinate along a complex contour, say like as indicated along in this picture, and then the branch cuts of you can kind of avoid the branch cuts in the Hawking modes, turn around the branch point and come back. So you end up with a spacetime with doubled asymptotics. And then the happy part of the story is that, like, you naively implement ADS-CFT rules, GKPW or whatever, and you end up like generating correlation functions which has the right Schwinger-Keldysh analytic properties, right? And the point is, we don't know how to really derive this. It's since the structure of the branch cut at the horizon and so on are true for general black holes in general spacetimes and so on. There's a logarithmic branch cut and so on. So this prescription seems to be a general prescription for black holes, but we don't have a way to derive it more than the fact that you can check that the AD-CFT rules on this gives you this particular correlation, the correct Schwinger-Keldysh correlation functions. And in general, there is this analytical continuation from this on this contour does is that it makes this horizon structure is kind of transparent, completely transparent to ingoing modes as when you compare across two sides of the contour, and the Hawking modes kind of suffer a Boltzmann suppression, frequency dependent Boltzmann suppression. And in fact, you can work out that general spin fields have a suppression which looks like this, and which, in the case of half integer spins, it means the Boltzmann introduce an additional negative factor on the Boltzmann weight. So basically the point is that if you any correlations, the thermal correlations which you derive with Boltzmann Bose-Einstein factors for bosonic fields, naturally, if you implement the same boundary conditions for fermionic fields, convert to Fermi-Dirac factors. And then there are two asymptotics, like I said, and then the top, the slightly positive imaginary asymptotics corresponds to the left part of our Schwinger-Keldysh contour.
I have a question. When you are saying that this e to the I 2 pi s takes into consideration whether the modes are fermionic or bosonic, isn't that an additional factor top of the already minus or plus one factor that comes in with the fermionic and bosonic mode? So shouldn't the
no. So remember, like, say if you're calculating 2-point functions, you are okay. If you look at it carefully, it doesn't happen. Maybe that's the shortest answer.
Okay.
Sorry, Akhil, I'm confused about your first point. Let me take the ingoing Eddington-Finkelstein coordinate, say, to be V, okay, just to be specific, and the outgoing to be U. Now, it's true that the tortoise R star has a log, and therefore, but that log will cancel out in V in my convention. So the ingoing mode is fine. The outgoing mode in terms of the U coordinate will have a log singularity, but I think of the Hawking modes as related to exponential of U, right? With the surface gravity. So what do you mean by saying the Hawking modes suffer from a branch cut?
Yeah, so the exponential of U with the frequency and so on, right? So that's indeed how you get the Boltzmann factor.
Yeah, but when you, just to understand the language, when you say the Hawking modes suffer from the branch cut, you mean the u coordinate before exponentiation.
So,
Is that
so
what
I work with UR. So then there's a logarithmic branch cut on the tortoise coordinate itself.
Yes.
But then the exponential behavior, like you said, like the e raised to minus I omega u or something. Though I work with VR, you can think about it in u coordinates. It does have r minus RH log r minus RH power omega kind of or r minus RH power I omega kind of behavior, right? Because because
Okay.
R star is really like a log.
I see.
So that's indeed how the Boltzmann factor comes when you
Now I understand. Sorry, I wasn't so clear. I see. And you're saying this analytic continuation allows you to go around that branch cut, and it's a particular way of computing them.
Yeah. So you can, So naively speaking, it's just it's a choice of coordinate domain for your black hole saddle. So this trivially satisfies Einstein equation, and then you have just redefined your radial coordinate to lie on this particular domain rather than some naive part of the real right line, right?
Mm-hmm. And the geometry, although now complexified, is a completely smooth geometry in the sense of the curvature invariance.
Yes, so it avoids the curvature singularity. Then it doesn't have anything beyond the horizon, but it has doubled asymptotics and so on. It's
quite nice. Yeah. Okay. Thank you.
It's like basically the fin part of this picture here.
Sorry, Akhil, is it clear that this kind of analytic continuation black hole solution would correspond to the precise contour in field theory that you want?
It does, like I said, there's no derivation, but then you apply ADS-CFT GKPW rules and then you calculate correlations, and they have a correct analytic structure which you can check even with interactions and so on.
What do you mean by they have the correct analytic structure?
They are say KMS condition. There are these consistency conditions because you can cycle operators through the thermal trace, right, and then which shifts the time and so on. So those conditions are like there's like straightforward argument to show that that is satisfied and so on, which I come to in the next slide.
So the KMS conditions, I mean, they should be satisfied from the black hole geometry and also in the field theory contour. You expect them
in the field theory, you know it should satisfy it, and then there's once you think of the black hole saddle in this way, there's a clear argument that even by general Witten diagram calculations should give you correlations with that structure.
But it could be that it is calculating something else which should also satisfy KMS conditions. Would it not?
Which would be like cleanly deleting sections which still make the KMS structure. Yeah. There's no derivation for the saddle. Sure. Yeah.
I see. But if you just, let's say, follow this contour all the way to the boundary, what do you get? Can you not trace it to the boundary field theory and see what is happening?
I don't know what you mean. Sorry.
Well, there is this geometry with some boundary, right?
Mm-hmm. So this is just a constant time slice. This is the radial contour.
Yeah, so exactly. So now this is happening. This analytic continuation happening in the radius.
Yes.
I see. So maybe so the boundary on the boundary there is no analytic continuation happening, right?
Right. So the boundary there is an analytic continuation in the time contour. And then in the bulk, it seems there is at least an easier prescription to implement the same analytic continuation is to analytically continue radius contour, right?
But it's a bit unclear then to tie to the boundary kind of transparently, right?
Yeah, it is a bit unclear how to think of this in the boundary or like.
And the Van Ries Skenderis picture, there it is that you cannot quite think of the bulk solution in terms of analytic continuation. You have to think in terms of some gluing, cutting and gluing.
Yeah, that's a like a simple cutting gluing, like how you typically glue manifolds and so on. Yeah.
Cannot quite think in. I see.
So they don't. So by what basically they lack is the structure of the horizon.
Yeah, I understand.
A smooth structure of the horizon, and the reason many of these interacting calculations can't be done in that prescription is also because they lack the horizon structure.
Nice.
You don't, so beyond the quadratic correlations, beyond the 2-point correlations, which in holography end up being boundary terms, right? So you just need some continuity in the bulk or something to derive those. But beyond that, anything which requires you to really integrate it and integrate a Witten diagram vertex, the structure of the horizon really is a necessity. Yeah.
Right. But is there a way to kind of intuitively justify that this is the thing that you wanted to do?
No, I mean, I think I was trying to write the slide in a way it is intuitively justifying. Okay, I don't know. No, I mean, answer is no. Yeah.
Okay, thank you.
And this is just a section of the wedge that you had in the previous diagram. I mean, this.
This is a time slice of the spin. This is a time slice of the pin. Yeah.
Yeah. So, but how do you take into account the lower part?
Which we don't. So that's still an open point. So we don't know how to obtain a similar prescription when your Euclidean geometry, the state is not the equilibrium. It's not the equilibrium black hole saddle of the cigar, right? So that's still an open point, like how to like go beyond this equilibrium configuration. How to prescribe something similar when you have a general black hole Euclidean saddle. Yeah.
But I thought when you're considering finite temperature, you have to consider the Euclidean black hole, right?
You can deform that state, right? You can put Euclidean sources or something and define non-equilibrium states, and then those states should also have a real-time dynamics, which will have some similar saddle, and then you would want to define this real-time saddle even in general non-Euclidean. Yeah.
Yeah. Okay.
Okay, so let me quickly go through some evidences for consistency of this prescription, right? So the statement is that if you are given ingoing solutions, which we have been computing for black hole saddles all the time, they can be promoted to Shingle-Keldysh solutions on the full contour by some prescription like this, where you have the ingoing solution here, and then there is the outgoing solution is given by some time reversal. Naively, the statement is that I'm studying ingoing Finkelstein coordinates, but it's secretly the same black hole saddle, and hence it has a u going to v, the time reversal isometry, which relates the ingoing outgoing time, and you can use that to generate an outgoing solution from the ingoing solution. And then if you want to have boundary conditions JL and JR on the top and lower part of the bulk contour, you have to have these coefficients JF bar and JP bar.
I have a related question. When you are saying that you're reproducing the correlators or whatever, the observables from the bulk point of view as well as the boundary point of view and the match, are you considering the full manifold, or just the part that you just said was necessary to do it? Because unless that happens, I don't see why they should match.
Full manifold, as in the Euclidean part is missing, you're saying? Yeah. So that really like so how would this calculation go, right? So I'm computing some effective action of the boundary, say some correlation generating functional. So so I can really think of it as working for a infinite stretch of Lorentzian time, and so in the bulk computations, if you put it technically, you just ignore initial time slice contributions.
So how do you perform the boundary calculation?
So you construct a solution which satisfies the correct boundary conditions on the real-time part,
right?
On the real-time part, because there is no sources you add on the, like I said, you don't deform the state out of equilibrium. So there's no sources you add or boundary conditions you prescribe on the Euclidean part.
Yeah,
which
you
would-
don't add any sources, but in order to calculate the thing, you have to consider the entire contour, right?
Okay, I guess the shortest answer is like we just integrate over the real-time part. I guess so. The I guess and the rest of it. So it you can think of it as some. Yeah, I guess we are just ignoring the initial time slice contributions, which is fine for as far as you are considering some calculating some generating function or something. It's, in some sense, you are say at least at the quadratic order, it is pretty clear that you can ignore them because you are not calculating the terms which are independent of the sources you prescribe over the.
What I'm concerned about is if you have finite temperature, then you have to have the lower part.
So you might be indicating that I need the lower part to get the correct boundary correct solutions which give the finite temperature correlations.
Yeah.
Which is not necessary in this prescription. That's the point. That this analytical continuation, that this boundary analytical continuation implements a boundary condition, and the boundary condition uniquely picks up the solution. And just from the asymptotic boundary, you ignoring the initial time kind of region, you get the correlations with the correct structure. So basically, this picks up a unique solution.
You're getting the correct structure. What I'm concerned about is why you're getting the correct structure.
Oh, of course. This is a prescription, right? Like I said, like it's not proved from a more general argument or anything. So the consistency, the evidences for consistency are the following. So I just wanted to, so this part you can, I just want to define this JF bar, JP bar. So there is, so of course, like I said, you have to check for Schwinger-Kelly's collapse rules, which is the fact that if you put JR equal to JL, the action vanishes, which says that terms which are exclusively made of JF bars in the action should vanish. And similarly, the KMS conditions, the full KMS conditions, the consistency is like similarly gives you a statement that terms which are exclusively made of P bars vanish, and which are both satisfied, and both of which you can argue in for general Witten diagram computations due to this analytic structure of the contour. And then a second check could be that the counter term structure, the counter terms you need to add to make your computations regular, like should factorize like this. There shouldn't be any mixed counter terms, and that is also satisfied, which is actually a tight check. And these papers were like which are the only computations in the saddle with interactions. This was shown, right? Like so there's this paper where we computed the nonlinear corrections to a Langevin equation, and there's this paper by Chandan Log and Mukund, where they study some interacting general phi n theory and calculate its endpoint correlations and so on. And then you would ask, okay, would this such a prescription work for a general black hole or more general black hole, and which has also been shown to work. So this has been it has been shown that a naive contour bending gives the correct structure for rotating as well as charged blackbranes. So if there are no more questions from this section, I will go to my next part, which is
Akhil, one quick question. One of the nice things about fluid gravity was that it was a non-linear thing. So far, what you presented seems to be like an amplitude fluctuation kind of thing,
right,
because it's all in the background of the original black hole that you're doing your calculations.
Yeah.
So now, I suppose you could excite fluid gravity solutions by turning on the classical part of the source and keeping the quantum part small. So I was wondering whether you could generalize what you've said to large classical sources and small quantum sources, if you know what I mean, sum and difference kind of things.
yeah, so I could in fact take one of the fluid gravity solutions which have a regular horizon and so on, right?
Yes.
And I could try to implement this program where I naively take the ingoing horizon and continue this and still check if that defines some.
And what would you be computing?
I guess I would be computing the real-time correlations when the state is defined by the fluid gravity configurations, right?
Okay. Yes.
So that could be an exercise, so we don't. So one thing about that is that like the fluid gravity, so all those things are there are various gauge choices and so on, which implements the fluid gravity program, right? But say the radial gauge and so on. So what we find is like because of some step like this, where you have to construct solutions by time reversing, etc. We stick to gauges which are time reversal nice, which is not really radial gauge. We want to work with gauges which are consistent with time reversal. But for the leading saddle itself, I guess you can take a fluid gravity solution, like which is written in some ingoing, almost like an ingoing solution, and you could do this contour bending, and you should that should give you something. I don't know if that gives consistent results. Yeah, you could do what you said. Yeah.
Thank you.
I don't really see any problem with it.
Akhil, I'm very, very sorry, but Shiraz, since Shiraz raised this, let me just, can you go back to that slide where you show the Skenderis thing? I want to just ask Shiraz and you, but it's more a question to flag for, say, a discussion tomorrow if Akhil, you'll be there. You know, Shiraz, what I was thinking, Akhil, when you showed this picture was, we know how to compute out of time correlators, say even for one side in your left hand diagram. You know, take the thermofield double. If I want to compute OTOCs, even by just inserting operators on one side, I know what to do. I have to turn on suitable boundary conditions on the time-like boundary of say the right hand side and the past horizon, right? And then I can do OTOCs, which means I can study contours which zigzag back and forths in time. So is there a way to do fluid mechanics in a full non-perturbative way where you compute, where you turn on suitable boundary conditions on the past horizon and the boundary and do Shiraz's construction for tubes maintaining regularity in the future horizon and compute all your out of time correlators, say of stress tensors? Okay, this anyway, does it vaguely make sense, Shiraz, or anyway?
I don't know, Sandeep. I've many times tried to make things like this precise without success, but I would love to be able to do something.
Okay, we'll talk tomorrow then. Akhil, come back for our discussion. Go ahead.
Yeah, sure. Yeah, be happy to. Yeah. Right. So then I can go to the second part of so I guess I have answered one question I motivated, which is the formalism to study these open field theories, right? And then the second part is about how do you really extract out the fluid modes from a general holographic plasma. And so we need a prescription which, or in other words, we need a prescription which separates out the Markovian modes and non-Markovian modes, the way I define them. And let's for the case focus on its d-dimensional CFT, right? So a working principle here seems to be that you can simply do an SO-d-2 harmonic decomposition of the modes. So what I mean is you go to a picture where the hydrodynamic modes, all of them labeled by some wave vector, because all hydrodynamic excitations are like gradients of some configurations, right? Like they are like spatially varying excitations. So they are labeled by wave vector. And then you can further label them by what fixes the scale. So you can, it's like the standard, it's like the Wigner little group kind of analysis where you fix a K and then you ask what representation of the transverse SOT-2 directions does the excitation fall into. So
sorry, could you briefly say what Markovian means, please?
For me, Markovian means any excitation of the CFT which doesn't have long range correlations. So you can.
So the things you want to integrate out.
With the things I want to integrate out. Yes.
Okay, thank you.
Yeah. So then you can do an SOD image.
Do you mean non-local in time? So you want to avoid
and space and space. I want to avoid anything non-local. I want to get boundary functionals which represent my the key object of interest, like the string action for the fluid modes, generating functional for the shortest distance modes, which is everything fully local. So for instance, when so anything integrated out, the demand is anything integrated out can be coupled to other probes acting on probes probing the fluid, but in the probes, probes then themselves shouldn't have non-local. Any integrating out shouldn't have non-local influence on the probes.
But
or the hydrodynamic modes.
If it is non-local in space, then why do we call it Markovian or non-Markovian? I mean,
I guess.
Yeah, sorry, go ahead.
How do you really make that distinction?
I mean, suppose you have some kernel, which is non-local in time, then of course, you cannot set up an initial value problem because things will depend on future times data as well. Then of course it would be non-Markovian. But if you go time slice by time slice, and at everything you have whatever amount of non-locality that you have in space, but given the data at t equal to 0, you can find out the thing at t equal to epsilon. So that's Markovian.
Well,
so maybe I can jump in. Non-locality in space and non-locality in time are related in relativity, right? I don't know. This may be a stupid statement, but I just wanted to make this statement.
Yeah, I don't see a distinction when it comes to this hydrodynamics, right? Like all the, basically these are long wavelength modes, and then you have they have a dispersion which makes the mode have long time correlations. But then basically the mode also has long distance correlations. So my statement is that I don't want to integrate out any hydrodynamic mode which have dispersion relations. So you can think of the gapless dispersions. So which means the dissipation time is proportional to the wave vector and so on, right? Or wave vector, some power of wave vector. And then I think that essentially means anything with non-local in time is also non-local in space. Maybe I can just say I want to do it this way. Like I want a description of the probes which is local in both space and time. Maybe that's the shortest answer.
Yeah. All right. So
I want a local field theory.
You have a reference background geometry.
Mm-hmm.
Therefore, you can certainly talk about some ADM evolution, and you can make a distinction between non-local and space. But okay, never mind. Maybe you are just calling anything non-local non-Markovian.
Yeah, I want a local field theory description. So that would restrict me to what I'm doing. Right?
It's semantics. I mean, that's not the usual notion of non-Markovian.
Yeah. So yeah.
That's fine.
Hello. So if I may comment about this thing, I think so Gautam, in this problem, the hydrodynamics, it is indeed true that things which are local in time and local in space are pretty much the same. It's the hydrodynamic modes. But what you're saying is indeed correct, and it is indeed relevant. Let's say, for example, if you're not looking at this problem, but you're looking at something like Lalanas and liquid theory, right? Or where the Fermi liquid theory is we can formulate them in space. We formulate in K space because there is a Fermi surface in K space, and that's important. And things are modes are local near the Fermi surface.
Doga,
right?
your audio, there's some problem. I mean, I can't. I mean,
Yeah,
I can
your voice is super distorted. Yeah.
I can only half hear what you say.
I think it just says something about my.
I think your microphone is super amplified. Like maybe if you.
Okay, maybe.
Yeah, it's cracking. So.
Is this better?
Yeah.
Yeah. Saying, this distinction between space and time non-localities is important.
Yeah.
This problem, but in problems like when we think about, let's say, if we extend this kind of framework to lambda Fermi liquids and so on.
Yes.
There, like there, it is indeed true that you have long-lived lambda Fermi liquid modes. Okay. But they are kind of localized not in space, but they are localized in K space. Right? They are localized near the Fermi surface. So in that case, in that sense, they are non-local in the X, local in K. Okay, but they are long-lived. Okay, so which means that like there are some finite cases. So in which case, like indeed it's not good to like think about small K expansion, because what we want to do in that kind of case is K minus K, small K minus Kf expansion, right? So in this case, it's not like local in space, because we're kind of not expanding about small wavelength modes, but long wavelength modes, but we're expanding about some wavelengths close to the inverse of the Fermi. So there are indeed situations where this distinction that you are saying is relevant, and we should be careful about it. But as Akhil said, like that's not relevant in this problem.
I see.
That's all the comment I wanted to make.
Okay. No, thanks, Doga. Yeah. Thanks.
Yeah. Thanks. Okay. So if there are no more questions, like I was saying, you can do a SOD minus 2 representation theory on these hydrodynamic modes, and then you would like decompose them into the tensors and the vectors and the scalars of these representations with so many modes of each kind. So let's consider an example to see what this does, right? So suppose you have a current, some U1 current, and you want to study how the charges of this current diffuse and so on. You can think of the spatial part of the current being split into a SOD minus 2 splitting like this, where I label some scalar part, there's some vector part. So one thing you see is the JV part is trivially conserved. And in some sense, that means that it should be a fast mode. And any non-trivial diffusive behavior is described by the scalar part of the current. For instance, you can think that, like, say when you have a magnetic brake or something, the magnetic brake works by like triggering circulating eddy currents, and then those are like this vector part of the currents, which kind of dissipate fast, and the brake works, right? So similarly, there's a decomposition for the stress tensor. You can do an SOD minus split of the stress. The tensor part of this is trivially conserved, and hence corresponds to fast mode, whereas the vector and scalar components shown long-lived behavior. And in fact, we know that the shear diffusion corresponds to the vector part of the stress, and the scalar part corresponds to pressure or sound waves. So the basic takeaway lesson being at the quadratic order, say in some effective action or in quadratic order in fields, SOD minus 2 decomposition seems to do what we want. Like it separates out different hydrodynamic modes. But then you can do a argument for the same from the gravity side, right? You can say that SOD minus 2 decomposition separates out bulk, Einstein, and Maxwell perturbations into gauge invariant sectors, and this motivates the decomposition from the gravity side. So the separate hydrodynamic behaviors corresponds to separately gauge invariant sectors of Einstein and Maxwell perturbations in the bulk. And then there is the standard perturbation formalism, where you assign a master scalar, work with these gauge invariant variables and assign a master scalar correspond to each of these sectors, and derive the gauge field components as from this master scalar. So essentially, you reduce every degree of freedom in the hydrodynamic sector, in the hydrodynamic theory, to a effective scalar in the effective scalar in the bulk. So every hydrodynamic mode in the boundary is dual to some particular effective scalar in the bulk. And there's some technical aside to this way of doing it, that why we want to work with gauge invariant variables, and why we want to really reduce the entire and gauge field dynamics to scalar dynamics and so on. But I guess I'll come back to it if there's a question on it or something, because it's a bit technical. So there are no questions till now. I will discuss on how we treat these scalar variables. I will discuss how we treat the scalar variables and how the different scalars.
I have a question. When you're talking about the Einstein and the Maxwell perturbations, they are in the bulk, right?
Yes, yes.
So they should be having an extra dimension.
Yes.
So how is that manifested?
First
of all, are they in ADS space?
This is in ADS space. Sorry, so I should have mentioned this is distilling out fluid modes, the gravity perspective. Right?
Okay, go ahead.
Sorry, Akhil, some very elementary thing. Why do you say it's only scalars? Why? I suppose you mean SOD minus 2. When you say scalar, you mean from an SOD minus 2?
No. I mean bulk master scalars, like where the standard scalar, there are formalisms where the d by parameterization, if you want to call it that way, of the dynamics in the bulk.
But aren't there things you might want to call vectors in the bulk?
No. Like let me just maybe say it here, like, right. So if you have bulk. So the bulk Maxwell fields as asymptote to boundary currents or sources, right? And then there are part of the Maxwell fields asymptoting to JV. There are part of the Maxwell fields asymptoting to JS. But then that's it. The components are completely ascribed to the VA part, right? And then the boundary value of that part itself is a JV and can be thought of as a bulk scalar. Maybe if that explains. It's basically doing a d-by parameterization of the bulk solutions.
Maybe what Shiraz is asking is, if you have JV times VI, then you have an index hanging out.
Right. So the index is stuck with the vector harmonic, and the JV part is what is characterized by the scalar master field of the bulk. Is that clearer?
Okay, so you say it's like there are some indices, but you get an equation for any one of the components.
Right. So it will be clear as I write the solutions in terms of the scalars in the next slide.
Yeah.
Okay. So the statement is you can reduce the bulk Einstein-Maxwell equations to separately gauge invariant sectors, and each dynamics of each sector is defined by a scalar effective or a master scalar variable, and these scalar master variables correspond to what are the sectors, right? There is a sector of the scalar currents, the JS. There's a sector of the JV, the vector currents. Then there are three of these: TS, TV, and TT. So the statement is all the master scalars in the bulk, which come from the TT, TV, JV, and JS. So except for the scalar perturbations of the bulk gravitons, have equations of motion which can be derived, which correspond to some action which looks like this. It's a dilaton coupled master scalar action with the dilaton profile defined with a simple radial exponent of the radial coordinate. Okay, So you can see that this is an action. If I put where I put m equal to d minus 1, it reduces to usual massless Planck order.
And this effective action should be thought of in 2 dimensions, r and t.
It should be thought of in full dimensions, like the full d plus 1 ADS.
Oh, but since you've already taken the SO d minus. Oh, I see. You're allowing it to move.
It has a frequency wave vector label. So this del is general general Klein-Gordon. This is a general Klein-Gordon action in the bulk.
I see, and including angular dependencies.
Including the plane dependence, yes.
Okay, thank you.
Yeah. So E power chi s is like some dilaton which modulates how the scalar is coupled in the bulk. So the case statement is if you assign specific values to this m, say d minus 3 and so on, it reduces to the effective scalar describing the corresponding Maxwell-Einstein fluctuations. So then there's a similar scalar description for the for the scalar type gravitons, by which I guess it's clear that I mean this graviton part which asymptotes to this part of the stress tensor, right? Which is more involved. It has a dilaton which depends on the k. It has a potential and so on. And the calculations are messier and so on. So which I won't talk about in this talk. Hence, I will mostly concentrate on these 4. And these 4 can be treated uniformly, and then based on the takeaway being that based on how this m is, these show the dynamics of the short-lived modes, and with a single m you can parameterize basically the dynamics and clearly see that how these modes correspond to short-lived and long-lived modes, etc. So I should have this is what you guys wanted. This is how you write the solution in terms of these fields. Okay, so the vector sources for the boundary sources. So the bulk Maxwell fields asymptote to the boundary sources, or the bulk gauge fields asymptote to boundary sources, and the source of the vector part of the current is given by phi d minus 3. Source for the traceless part of the stress even is given by d minus 1, and the other part, the scalar part of the current is given by the scales. So I guess in the bulk, the bulk Maxwell fluctuations have this part corresponding to the scalar part of the Maxwell fluctuations. Sorry, I think I misspoke. Give me a second. So basically this is a solution. This is the bulk solutions written in terms of the scalars. And these scalars are essentially described by an equation of motion which came from the action I motivated last night, right? And so is that clear, like what I mean by the
sorry, not to me. I mean, in the vector sector, for instance, why do you have just one scalar? You should have as many degrees of freedom as there are vectors.
Yes, but they all have the same equation of motion, right? There's a rotation symmetry.
So that's fine.
So okay, so there's a sum. Okay, so maybe I missed that up. So there is a sum over the different vector harmonics.
Phi I d minus 3 here.
There is a phi j, say let's say phi alpha v alpha, where the alpha runs over d minus 2 vector harmonics, right?
Okay, fine.
Yeah. Sorry, so maybe that was the confusion. Sorry.
Yeah. Okay.
Similarly for the tensors. Yeah.
I thought the phi's and the other things, the phi d minus 3s and the phi d minus 1s, they were like the j's and the t's of the previous slide, right?
Yes, they asymptote to that. But then there is, since there are so many tensor-like perturbations and so many vector-like perturbations, there's an index which had to be summed over, which I have omitted here. Is that what you asked?
The sources were scalars, so how come they'll suddenly acquire some index?
The sources are not scalars, right? Like,
no,
you have a source for each of the vectors.
Yeah. So for instance, you have TS is a scalar, TV is a scalar, and so on and so
yes,
forth. Yes,
right? That's right.
JS, JV are all scalars.
Okay.
Yeah.
So what?
So those asymptote. No. So the bulk fields asymptote to those in the boundary, right?
Right.
So on the boundary, now go back to So on the boundary, go back to So on the boundary, the phi's should be the things that correspond to the j's and the t's.
So it's let's say the vi and tij, right? So indeed phi d minus 3 labeled with an addition alpha to count the harmonic, okay, or phi d minus 1.
I don't understand where the harmonic is coming from. Why should the harmonic come? Because
this I'm writing the bulk gauge field, right? So that has obviously has indices. Maybe I'm not getting what you're asking.
Your j's and t's were scalars, right?
Yes.
And they were sources on the boundary.
They were sources on the boundary. So j's and t's themselves had an index labeling which choice of the particular harmonic.
So those are implicit in those expressions.
Those are implicit in the expression. Sorry for the confusion. Yeah.
Okay. And another thing is another thing that I don't understand is how come the boundary fields, not the sources, the boundary fields and the sources are appearing at the same time on the right hand side, because on the left hand side you just have the bulk fields, right?
Okay, left hand side is just the bulk fields, right?
You have just the bulk fields. So the bulk fields are dual to the sources on the boundary, right?
Right.
So I don't understand how the bulk fields are how the boundary fields are also appearing along with the boundary sources.
Which one are you calling the boundary fields?
The VIs and the TIJs and so on.
No, VIs and TIJs are the harmonics, right?
Harmonic. Okay.
Sorry for the mistake. So VIs and this map, the bold letters correspond to harmonics.
Okay.
Does that clarify it?
Yeah, I guess,
yeah. Okay. So notice that, like, or in any typical dimension, the first components, right, which I earlier motivated are Markovian excitations, come with a scalar which have the m plus 1 greater than 0. Okay, and then the non-Markovian components, which I motivated as scalars and vectors and so on, respectively in Maxwell and Einstein cases. They come with scalars with m plus 1 less than 0. So for the following discussion, for the time being, I'll just quickly call these scalars with m plus 1 greater than 0 as Markovian and m plus 1 less than 0 as non-Markovian. So
m was this coefficient in this.
M was this.
Okay, thank you.
Yeah, m was some R exponent designed such that when you put it to d minus 1, it goes to the master triangle action. Okay. So which you can see, right, where I see the t tensor is d minus 1, which we know that the traceless part of the shear satisfies an equation which is same as that of the master triangle. Okay. So in the examples presented, like standard GKPW prescription for the correlation generating functional for the CFT, which is non-normalizable boundary conditions, which are sourcing boundary conditions, implements Dirichlet boundary condition on Markovian scalars. These guys, you can see that the sources, the boundary value of the sources are given by the boundary value of the scalars I motivated, and Neumann boundary condition on the non-Markovian scalars. So you see that the boundary value of, say, the AV component, or in this case, the GVI, the HVI, is given by the conjugate momentum of the bulk master scalar. So if you calculate the conjugate momentums, then this statement flips. The boundary operator expectations are given by the conjugate momentum of the Markovian scalars and boundary value of for the non-Markovian scalars. Okay. So basically, if you want the field strengths corresponding to this VI, you want to take the conjugate momentum for 5d minus 3, and if you want the stress tensor component, you want to take the conjugate momentum corresponding to 5d minus 1, and ulta for this part, where you can see that the field strength itself in the bulk, if you calculate from this particular gauge potential, happens to be the value of this phi 3 minus d, the radial field strength, right? Happens to be the value of this phi 3 minus d at the boundary, and the value of this phi 1, similarly for the metric perturbations. Okay, so we can quickly, like, it's a way to remember this. It's like there's a table. There are Markovian scalars, where the scalars which are defined to be the scalars indexed with m plus 1 greater than 0, and the non-Markovian scalars, which is our case. So in the standard cases where these appear, where if you remember m was plus or minus d minus 3 and m was plus or minus d minus 1, the sources are given by the boundary value of phi m for Markovian, and operator by the conjugate momentum, which I label as pi m. And in the non-Markovian case, it's the other way. So the statement about, so then you can hold that dictionary for a while, like, and then just look at the bulk solutions for these general M scalars, right? And the statement about these solutions is that their conjugate momentums have derivative expansions all the time. So you start with an action defined. You start with an equation of motion defined by the action I showed. You solve them, and then the conjugate momentums have a derivative expansion for all time. And at the boundary, there is a dictionary like this. The pi m looks like some polynomial km omega k multiplying the boundary value phi m infinity, right? So the boundary value of phi m, and then you can calculate these km's to some order, like we have them to some orders in derivative expansion, some third order or something, and it's in the general m case, and you get a polynomial of this type. Okay, but now when you put that result back into this table, right, what it says is that therefore operators corresponding to Markovian scalars, the pi m's, have no long distance correlations. If you want to write your operator in terms of the boundary value of the phi, which is the source, it has a local expansion in space-time derivatives. And in the non-Markovian case, the source is given as a local function of the operator, because now you flip what is the operator and source, right? In the non-Markovian case, the source is given by pi m, and what this relation then is it is a dynamical equation for the field. The phi m itself corresponds to the phi m asymptotes to the operator's expectation in the boundary, and this says there's a particular differential operator you can act on the operator expectation to get the corresponding source. So in the holographic way to think about it, like pi m's, this relation relates the non-normalizable coefficient and the normalizable coefficient, and the interpretation kind of swaps based on whether you are looking at a Markovian case or a non-Markovian case.
Akhil, now I'm very confused. Oh, sorry, go ahead. Someone else had a question, but I'm very confused. Maybe after that question, let me ask mine. Go ahead. Who was it? I'm not sure.
No, Sandeep, it was me. I think I'm asking the same thing that you're going to ask. So let me ask you.
Yours will be more coherently phrased. Go ahead.
I doubt it.
As always. Go ahead.
But the way I usually think about the phenomenon you're describing is that either in some sectors there are light quasi-normal modes, and in other sectors there are no light quasi-normal modes.
Right.
Those which have no light quasi-normal modes are the ones you're calling, I think, Markovian. And those that have light quasi-normal modes are the ones that you're calling non-Markovian.
That's right, yeah.
Okay. Now, I can't understand the connection between this statement about quasi-normal modes and the way you phrased it.
Yeah. But Shiraz, no, thank you very much. But let me ask an even prior question. Akhil, go to that previous slide where you were, okay. Now, let me ask you, okay, sorry, then we come to Shiraz's question. Now, in plain language, the last term in a mu dx mu, that last term at least involves the radial component, AR, isn't it?
Yeah.
You mixed it with dV, I guess. But I mean, if I'm just doing in a very simple situation, ADS CFT, let's say just with no black hole or anything, I could always choose a radial gauge and set AR equal to 0. And then I would just have the AI components, which would correspond to the boundary current, right? And then I could compute those correlation functions or whatever. Now, when you are allowing for this additional component and you're calling it non-Markovian, is there an analog of that? And then we can go to Shiraz's case, but just in pure ADS CFT without a black hole, empty ADS?
See, I'm not, so it's a gauge choice, right? Ultimately, it's a gauge choice. I'm not
so that's
turning on anything really. It's
why
a
not
gauge
set
choice.
it to 0? Why don't you set it to 0?
Right. So this is the technical aspect I was kind of skipping over, that like these calculations are ideally done in some, not in radial gauge. Radial gauge is a pretty bad thing, gauge to do these calculations, because there's a step which I kind of quickly went over where you take an ingoing solution and time reverse to get an outgoing solution. And that particular structure of and that particular form of writing the solution is ideal to see the correct where the Boltzmann factors pop up and how the particularly that JP bar JF bar combinations are motivated, right? So the statement is radial gauge is not ideal for that time reversal step, because the time reversal changes the gauge. But what we stick to is what we call the debye gauge. As you can see that there is no spatial AI which came with a del IS. Ideally, you could have had a component which spends like del I of the scalar harmonic. But that's the gauge we choose, where we switch off those components, and that's a time reversal invariant gauge. So that's the answer. Like radial. So the one lesson about like, okay, so this is part of the.
But just to say, sorry. Okay, it's a nice gauge you choose, but the spectrum, if I compute for all the quasi-normal modes, just to will be the same as I compute, that's some gauge invariant object, right? And then is it, just to now come to Shiraz's point, that the non-hydrodynamic modes, all the gapped ones, some of them in your gauge appear in the second set of degrees of freedom, is it?
The non-hydrodynamic modes appear as the VIs, the vector harmonics, right? These are the trivially conserved part of the current. Yeah.
So where are the hydrodynamic modes?
The scalar part. In the Maxwell case, it's a scalar.
It's this.
Yeah.
No, then I'm very confused. No, I mean, Shiraz, no, then why are you putting non-standard boundary conditions on the hydrodynamic modes?
So as of now, I haven't mentioned the boundary conditions, right?
Didn't you say that you reverse source and...
right, which is very visible from here, right? The boundary value of A mu is the conjugate momentum of phi 3 minus d, because these are derivatives acting on phi 3 minus d. So this parameterization using scalars comes with that statement.
No, I know, but I can do standard ADS at least. I've always done standard ADS CFT even for hydrodynamic modes. If you just compute the viscosity or something, you just, do standard ADS. You have a clear notion of what is source, what is response, and, you compute endpoint correlators, 2-point correlators. I'm a little confused by the terminology you're saying, where you reverse source and operator and so on. I don't know. Shiraz, maybe you had something else in mind, but I didn't.
No, it's related. I think what they're doing is parameterizing these. I think they're saying that standard ADS CFT with standard conditions on the fields we normally deal with translate to funny boundary conditions on these effective scalars. Is this right, Akhil?
Yeah, that's right. Like it translates to unusual boundary conditions, but then it has a structure to it as we come to it.
I see. So if you, sorry to interrupt. So just to say, at least if I were doing standard, a few point correlator calculations and working with a standard radial sort of gauge, I would use the usual boundary conditions. But in your choice of gauge, you would have to put these funny boundary conditions.
The point is the way the saddle is, the ideal gauge to work with is this, because you want to, yeah. And one thing is, first of all, we don't one way to introduce these here of course I have written out the gauge field components, but there is a way to, at least in these sectors, these 4 kind of perturbations, there's a gauge invariant way to introduce the scalars. What you see is that these components, as you can see, don't shift under gauge transformations because these are vector harmonics and tensor harmonics. They don't have gradient. They can't be deformed by derivatives. But then you can directly introduce this scalars in terms of the field strengths or the curvature invariance in the scalar sector. So that's one way to say it. The curvature invariants are can be defined to be proportional to this scalars. And then you can choose a debye gauge and the debye gauge, as I defined it some time back, and invert for the gauge potentials. So in fact, the way you introduce the scalars is gauge invariant.
See, can you just once, I won't slow you down, then you go ahead. You just show me what is your debye gauge just once. Sorry.
Which debye gauge is a statement that there is no perturbation with the del is. So I could have had a vector potential with del is dxi, right? I don't have those guys here. Similarly for the gravitational perturbation.
Is it just that the divergence free that VI is divergence free?
It is the divergence free.
Yeah, that's what I thought you were saying. That's what you mean.
Okay. Oh, sorry. Yeah. Yeah. So VI is the divergence free. Similarly.
Yeah, that's what I thought you were doing. Okay.
Yeah, okay.
Fine. I understand. Go ahead. Okay, go ahead. I can't say fully, but okay, go ahead. Mm-hmm.
Sorry. So Sridhar, you were asking a question, right?
I was saying that, existence or non-existence of light quasi-normal modes is what in my mind distinguishes hydrodynamic and non-hydrodynamic modes.
Mm-hmm.
And you've got some other way of wording the distinction that I haven't completely internalized, but I wanted to understand that these were equivalent. In particular, right, like the Green's functions, if you compute source to response,
mm-hmm,
non-analyticity of those, I suppose, is what distinguishes us, right?
Right.
So what you're saying amounts to saying that these Green's functions were non-analytic.
So what I'm saying amounts to saying in the Markov, what we call as the Markovian sector, this Km I write down happens to be the Green's function, and in the non-Markovian sector, the Km happens to be the inverse Green's function, which you can see where I just swapped the operator source mapping corresponding to the field.
I understand. So now both of them are small. Both of these quantities are small at small omega.
Both of these. So there's let me just say there's a relative factor, and then at small omega, of course, the Km is small. It has a expansion.
Yeah.
But then
therefore the inverse is large, and therefore
therefore the inverse has a pole and all that. Yeah.
Okay.
So basically the swapping what is the operator and what is source. Implements that like the diagnosis you mentioned for hydrodynamic modes.
Yeah, I understand. Thank you.
Yeah. What is it? Explain, because I always thought, I can do hydrodynamics calling sources. I don't know. What does this mean?
All I'm saying is, as well as I converted my bulk perturbations, fluctuations to these scalar variables, FT scalar variables.
Yes.
And then when you do that, you just observe that all these scalar equations, effective scalar equations, come from a single parameter class of family of actions. Okay. So you just go ahead solving them with this single parameter.
Fine.
And then what you see is that decomposition, how it distinguishes hydrodynamic and non-hydrodynamic modes is by basically swapping what you mean by operator and source.
In your gauge, this is what happens.
In this gauge and so on, and this gauge is not a choice, right? It's also like the time reversal isometric time reversal invariant gauge is something you need to work with in these backgrounds to clean these events.
Okay. So in this gauge, you're saying, look, there's something very preferred about the hydrodynamic modes.
Yeah.
They are the ones where you have this swap between the operator and okay, fine.
But particularly a formalism where you have done away with all the gauge redundancies and then you're working with effective scalar degrees of freedom. So there's one scalar for every excitation kind of situation, right?
And you're planning to deal with interactions also using these gauge invariant degrees of freedom?
Yes.
You know, I always thought this is what one was not supposed to do, right? The general relativity was simple because at nonlinear level, because one used non-gauge invariant degrees of freedom. This sounds a little bit like you're trying to reformulate general relativity in terms of gauge invariant degrees of freedom.
Yes.
Which sounds like what we learn in college we're not supposed to do.
Perturbation theory, no? I thought, Akhil, you're just saying.
Yeah, so I will be doing scalar perturbation theory.
Will be fine, but if you want to do something genuinely nonlinear, it'll be a horrible mess, right?
It will be, I guess, but then like I'm also not generally supposed to do nonlinear stuff with. General nonlinear stuff with general relativity, you know?
Oh, why not? In classical general relativity, we do nonlinear stuff all the time. Fluid gravity was nonlinear.
Okay. I guess, the way I phrase it is just some scalar action, like this action, and then additional scalar perturbations. So to any perturbative,
I have no quarrel with perturbation theory. You can certainly do it. I just feel that if you try to go completely nonlinear with this formalism, it's like trying to work with fluid dynamics in the basis of sound wave, in the basis of coefficients of sound modes and shear modes.
Right, it is, yeah.
Much nicer to deal with Navier-Stokes equations,
right? No, I mean, you need to go to some field kind of description to do the full calculations of like field fluctuations and loops and so on. No,
you're saying that you're forced to do this to do quantum stuff. Classically, it's much nicer to lead with Navier-Stokes equations, where the modes are the velocity and the pressure, or the velocity and the temperature.
I'm not sure. Like I think
the amplitudes for sound perturbations and shear perturbations, you could do it, but it would be a crazy thing to do.
I guess I don't. I guess when you go to the field theory calculations, say like which includes fluctuations and so on, like I don't know if there's any advantage of having velocities running in loops and that kind of stuff. I don't know.
Yeah. Okay. So you're saying that this beautiful classical simplification you're going to have to give up when you do not.
It seems, yeah.
Okay. Thank you.
Yeah.
I'm confused about something. I thought this PMs were the conjugate momenta for the phi m's. Is that correct? The pi m's
were the conjugate to the phi m's.
Yeah. So now you're saying that the pi m's are also non-Markovian.
What I'm saying is that
now you're saying that that the pi m's source the phi m's and the phi m's source the pi m's.
I'm saying the dictionary
momenta source the fields.
I'm saying the yes. I'm saying the dictionary of what is sourcing and what is the output changes across the sectors. Yes. But that is evident from this, right? Once you write this answers for the potentials, it is clear that the boundary value of the bulk fields in the non-Markovian sector are given by the pi m's. So pi m's are simply some d plus acting on pi 3 minus d or pi m's, right? It's some radial derivative, the conjugate variable, and
so you're saying phi 3 minus d is conjugate to phi d minus 3.
No. Sorry. What I'm saying is there is a conjugate variable to phi 3 minus d, which is pi 3 minus d, which is defined as d plus acting on phi 3 minus d. right?
Yeah.
And
E plus,
and
plus acting on phi 3 minus d. Okay.
yeah, it's some radial derivative combinations. In our case, d plus acting on phi 3 minus d with with some factors and so on, say r power 3 minus d factors and so on, right? Which takes out the scaling and so on, right? So in the case of non-Markovian perturbation or the scalar sector perturbation, which I'm like circling,
okay,
the A mu, the vector potential itself was given by pi 3 minus d. And hence the asymptotic value of pi 3 minus d is what you interpret as the source via IDCAT.
Okay, so now I get it. Okay, fine.
Yeah. Okay, so basically, so this is a distinction as you swap the dictionary, or as you since there's a Neumann-Dirichlet difference on boundary conditions on the GKPW standard GKPW boundary conditions, you end up interpreting this relation in two different ways. In one case, it shows there's a local. In one case, the Km happens to be the Green's function in the Markovian case, whereas in the non-Markovian case, Kms are inverse Green's functions. And then you immediately see that the Km is a diffusion, is the diffusion pole for a general class of diffusing operators. And you substitute m equal to d minus 1 minus d, you get the shear diffusion, or you substitute m equal to 3 minus d and you get the charge diffusion, and so on. So this at a go derives the result for some general class of diffusing scale operators and across dimensions and so on. Yeah. But we can take a step back, and then we can just think about the action, the m parameterized action I showed you guys. So you can just look at the solutions of that action, and it will have like any bulk equation of motion. It will have a leading an asymptotic solution which is growing, and an asymptotic solution which is decaying, and so on. So at that level itself, many of these statements. So now maybe I'm taking a step back and then and not restricting myself to the specific values of m's which showed up in the holographic context. I'm talking about this some operators, generic operators labeled by this m, right? So in that case, the Markovian scalars, again I remain Markovian scalars is m plus 1 greater than 0 defined to be are scalars with ingoing modes always non-normalizable. What you find is the ingoing solutions are always non-normalizable, implying they are triggered by boundary sources. So if you want ingoing or dissipating configurations of these bulk scalars, you have to have a source at the boundary. They have a growing boundary condition, and hence these operators quickly dissipate when sources are turned off. And only Hawking modes are normalizable, implying these modes do not characterize hydrodynamic configurations. You don't have ingoing nice configurations which can label your hydrodynamic configurations of the boundary. And for the non-Markovian scalars, some ingoing modes are normalizable when their frequencies satisfy specific dispersion relations, which is the case that the growing modes of this m plus 1 less than 0 scalars vanish if you tune your frequencies and wave vectors to satisfy that other relation we had in the last slide, which is as km equal to 0. And hence such frequencies, such modes with frequencies satisfying dispersion relations can be triggered without applying any source. And so they should generally correspond to some on-shell modes of the fluid.
So sorry, Akhil, what did you mean when you said only Hawking modes are normalizable? I mean,
so if you want a normalizable solution in these
Markovian sector,
in the Markovian sector, they are outgoing modes at the horizon.
But you mean they are normalizable? So they're time.
They're normalizable as in they asymptotically they like all decay or they show the suppressed asymptotic behavior.
Yeah, sufficiently. So regular at the horizon and irregular
at the horizon, asymptotically like vanishing or like showing the subdominant behavior implies they are irregular at the horizon.
Oh, I see. With your log singularities.
Right.
Okay. I see what you mean. So irregular at the horizon, but decaying at the boundary, therefore normalizable. But are they normalizable? I guess that's the point. The irregularity at the horizon keeps them normalizable with respect to some L2 kind of norm, because you would work it out in the
so I guess okay.
Is that's the point.
By normalizable, I just mean the asymptotic growth. I don't mean to really have evaluate a norm in the bulk, because this is some Schwinger-Keldysh double kind of thing, no? I don't know if I should think of it like that. I just mean the growth.
Hawking modes will probably be normalizable when.
Yeah, but this is a analytically continued saddle, right? I don't know if I should be calculating Klein-Gordon norm or something in this. Yeah.
Okay. So you just mean the fall off at the boundary.
I just mean the fall offs. Yeah.
And I can see these modes are normalizable in that sense. Okay. So that's what you meant there. And in the non-Markovian, which is where your hydrodynamic modes sit, you say there you do have some normalizable modes.
Yeah, so it means that if you can always have, you can populate the state with these modes which satisfy the specific dispersions without providing any additional sources.
Right. This is your fluid mode.
These are the fluid modes. Yeah.
Okay, I'm with you. Go ahead.
Okay. So the
and Akhil, the K that was running through your discussion, the K, that's why you had an SOD -2 rather than SOD -1. That is in the source. The K is in the are in the sources.
K's are the Fourier momenta, right? So maybe sources? I missed of the sources, operators, everything. This is like at the level of linear response, right?
Right. Thank you. Yeah. So you're turning on sources with some K and then. Right.
Yeah. So K and omega, right? You have to tune omega K to satisfy the dispersion relations. Right.
Okay. Thank you.
Right. So the story so far suggests a natural boundary condition prescription that gives local boundary functions. Dirichlet boundary conditions for all scalars, right? For generically like the scalars, the M-deformed dilaton scalars, you could apply Dirichlet boundary conditions. This implies one has to fix the operator values constant in the non-Markovian sector. So these are okay, which is not what you do in the usual GKPW, right? You fix the sources. But this is natural from the field theory point of view, as we want to derive the effective action for the modes with long distance correlations. So you don't want to really calculate a correlation function as we usually do in ADCT, but you want to Legendre transform that correlation function and write it as an effective action for the field expectations, right? But in the Markovian sector, you can do the usual thing. You can indicate them out. And so we call this resulting object a Wilsonian influence functional because we have indicator of the fast modes. So this would be like qualitatively, like schematically, it will be the Schwinger-Keldysh action with the Legendre transform performed to make it an effective action. So you take the Schwinger-Keldysh generating functional, which is a function of the non-Markovian sources and non-Markovian sources, and Legendre transform only the non-Markovian part and make it into an influence functional for the non-Markovian.
Akhil, I'm telling you how I'm understanding what you're saying, at least roughly, and you tell me if this is okay. No, I mean, we want to deal with some local object. When you integrate out massive degrees of freedom, just the correlation functions are local, so you're fine. But if you've got massless degrees of freedom in your problem, if you integrated them out, you would get something non-local.
Right.
So then what the usual rules are that we should deal with not the correlation functions of these massless degrees of freedom, but the effective action of the massless degrees.
Right. That's all I'm saying.
That's all you're saying, right? Because the Legendre transform changes from a effective action to correlation function.
Right.
So where you have massless degrees of freedom, don't deal with correlation functions, deal with the quantum effective action.
Right. Okay. Exactly. Yeah. And one nice thing about this formalism is that so so like I motivated here, there's a boundary condition changing Legendre transformation. In the field theory, this is the Legendre transformation from correlation generative functionals to effective actions. And similarly, from the gravity side, you will have to add boundary terms which correspond to boundary condition changing Legendre transforms. And viewed from the effective action perspective, right? What we find is that you don't have to bother. You just have to the correct Wilsonian influence functional is just given by taking the M deformed M parameterized action and implementing a Dirichlet boundary condition on all scalars. So somehow this action by itself will have a natural Dirichlet boundary condition, right? Like a quadratic action in the bulk. And that seems to be the right Wilsonian, low energy FT theory object, which kind of is nice. And this is the central object we like. So just to conclude, this Wilsonian influence functional parameters in terms of fields and sources based on non-Markovian or Markovian is the central object we want to calculate in these things, which describes the low energy FT theory. So that's it.
So it sounds like you're computing some sort of effective action for hydrodynamics.
Yes, I'm calculating the effective action for the hydrodynamics, and then this relation I gave you here derives the effective equation for these hydrodynamic modes.
Yeah, and let me understand what the variables in that effective action.
Mm-hmm.
In previous work by Loga and Mukund and Hong, these guys have tried to invent some nice nonlinear variables for these effective actions for hydrodynamics, with these diffeomorphisms and various such things. What is the connection? Your variables seem very perturbative. I want to understand the connection between these two. Maybe it's not a very well-formed question, but excuse that.
I guess they always think about some fictitious fluid at the horizon and then getting mapped to the fluid coordinates and so on, right? I don't know really what is the connection. I don't know, since Loga is here since week, maybe he can answer. I don't think there's a well understood connection.
Yeah, I don't think I don't think any of us understand fully the connection. I think that connection is yet to be understood. I think how it comes from ADS-CFT. That's what you're asking, no, Shiraz?
Yes, that's right.
Yeah, we like all that formation to come from ADS-CFT, but as of now, because that, as you say, it means you have to go for the full nonlinear formalism, and somehow you have to kind of square it with the practicalities of doing this ADS-CFT computations, which has not been done.
Okay. Thanks.
Yeah. But we'd like to do it. Not done yet, but I think it's in principle doable, definitely. We have to do it.
I have a question. In this expression for the K omega K, Km omega K, where is the K?
Okay. So the Q's are the K's scale with some temperature factors, and this frac W is the omega. So maybe I should have written frac WQ. Sorry, Q's are the K's with scale with some temperature factors. Okay. As you can see, this is with such that they are their dimensions are set to 0, right? Yeah.
Dimensions are set to 0. Whose?
As in, I'm adding omega and Q square, right? I'm just saying these are dimensionless scaled omega and K's.
Okay.
Yeah.
This is supposed to be the Fourier transform of the Green's function, right?
Right. In one case, it's a Fourier transform of the Green's function, and in the other case, the inverse Green's function. So this is the inverse Green's function of the non-Markovian, scalars, right?
Inverse Green's function, okay.
Because you invert it, I get a pole kind of.
Okay.
Yeah, which is basically this equation and this table, right? Yeah. Okay. So if there are no further questions, I go through my summary and directions. So we motivated formalism to distill out fluid modes with different hydrodynamic characteristics, and then we derived this object called Wilsonian influence functional for the long distance modes, and sources coupled to short distance modes. So then there are like various immediate future directions, most of which we kind of went through during the course of the talk, like derive the gravitational Schwinger-Kelly saddle, maybe from a more ADS-CFT bulk argument, and then hence the like, and there like hence from there like maybe define it away from equilibrium, say like turning on gravitational interactions and so on. Yeah. That's it.
Okay, Abhijit had to leave early, so I've been promoted to host. So let's thank Akhil for a fantastic talk.
Thanks.
Further questions or comments?
Yeah, maybe let me ask a vague question. So when Shiraz, Loga, Anthony, these people first started doing this fluid gravity, so it was not clear at the time. So Shiraz, you can correct me, that Hawking radiation can be brought into the fold, because Hawking radiation was something of a lower order in 1/G Newton counting. So somehow it's furthermore Hawking radiations of course had this different behavior at the horizon. They were not, I mean, something that you discussed, Akhil, which is that they are not smooth like the Eddington-Finkelstein mode. So the so maybe that aspect is taken care of, that you can handle things with branch cuts at the horizon and so on. But what happened to the Newton's constant coupling? I mean, counting. This is related to Shiraz's question about back reaction from Hawking modes. And is it like you are thinking of a large number of flavors of the Hawking mode so that their energy density can compete with N? Is that the?
See, I guess it's a consistent derivation of a Schwinger-Kelly action, right? Like, so at each order, when you derive an action, like there are these various vertices, like the Hawking vertices in the, say, the fluctuation vertices and the average vertices in the boundary, and then there's a consistent derivation. But it's
no, but aren't you always in the probe approximation, in the sense that
we are in the probe approximation, but then you can study perturbatively deform the saddle. Yes. So yeah, maybe okay. Maybe one way to say it is like, say you were trying to see. It's true that in this talk I was like talking about hydrodynamic perturbations or something, and let's just focus on the Maxwell part, or let's just focus on just a scalar, just some different scalar of the bulk, or some scalar operators, and its corresponding Hawking radiation and so on in the boundary or in the bulk. So then that perturbation theory is like then not really controlled by G Newton. So maybe I'm understanding your question as like
I'm just surprised that there seems to be some kind of a classical description of this Hawking mode.
Yeah, but that itself okay. That itself is fine, right? You also okay. Yes, you're worried about the classical description of like.
Yeah, I always thought that Hawking radiation, like the Hawking energy density and so on, these are some kind of one loop effects. If you were doing some gravitational saddle point calculation, then the black hole metric and such things, they would be the leading saddle point, and Hawking radiation and stuff, they would be about the log determinant of fluctuations around that.
Yeah, but
And
then
uh-huh.
I guess that's like you can ask the same question in field theory also, right? Like in field theory, the like the fluctuation effects are like suppressed, but then in the Schwinger-Keldysh action, you will a consistent Schwinger-Keldysh action would have these terms show up at the same order of fields.
At the same order of large n.
Same order of fields. Like so, these terms will have will be suppressed by 1 by n or something. But like in the field theory calculation, the Schwinger-Keldysh action would have terms corresponding to fluctuations and terms corresponding to leading dissipation at the same order of fields. Okay, so give me a second. What from the bulk you want to give me a second. It just okay, I guess I lost that thought of train. Give me a second. Sorry, train of thought.
Go ahead. We can discuss later. I mean, if this
yeah,
is...
I guess yeah. Let me phrase this better. Like
yeah, let me also try to.
You know, Akhil, and I mean, Loga, if you have the time, we have this discussion session tomorrow at 11 p.m. the virtual tea session, and if either of you or both of you could be around for that we normally discuss the previous day's talk.
Mm-hmm.
So if you and think issues arising out of it, so if you guys can be around for it, that would be very helpful for us.
Yeah, sure.
Yeah, we can be around. Yeah.
Thanks, Loga.
Yeah.
Okay, other questions? And of course, anyone who's interested in joining is welcome. These virtual tea sessions are open to anyone who's interested, anyone in the Indian physics community is interested. Any other questions?
I have a question regarding the K and omega K.
Mm-hmm.
So you're saying that once the K and omega K itself is acting as the Green's function, and once its inverse is acting as the Green's function, is that right?
Right.
How is that possible? Because
so that was the swapping boundary interpretation of the conjugate and field kind of thing, right?
What I'm concerned about is, suppose you have some Green's function 1 by x to the d or something, some d, and then when you invert it, it becomes x to the d. Is that correct?
When you invert it, you get a kinetic operator kind of thing, no?
Yeah, you get a kinetic operator kind of thing, correct?
Which is local.
So,
so you can maybe say it like that. The local kinetic operator gives you a non-local Green's function. Yeah.
So at one place it plays the role of the Green's function, and in the other case it plays the role of the kinetic term.
Yes. Yeah. Kind of. Yeah.
But then I don't understand. Okay, fine.
Okay, any other questions? Okay, if not, let's thank Akhil for a very clear talk. Thank you very much, Akhil. Thanks again, and see whoever's interested.
Yeah, thank you guys for having me and all the questions.
Bye.
Yeah.